Good afternoon to everyone. Welcome back to our third session. Just to remind that those ones who don't have the certificate, please go to the secretary. We have already your registration, your certificate. So in this third session, we have with us Professor Claudio Ruggieri. Is that right? Okay. And Professor Claudio is Professor of Structural Engineering and Fracture Mechanics at the University of São Paulo, Brazil, and is the Principal Investigator of Fracture Mechanics and Structural Integrity Research Group at the USP University of São Paulo. So Professor Claudio received his PhD in '94 from Osaka University, where he worked on fracture assessment of welded structural components and experimental fracture mechanics. His research focused on the development of defect assessment methodologies for deep water subsea structures, including submarine flow lines and steel risers. Professor Ruggieri has published in the areas of fracture mechanics and structural integrity, contributing with more than 75% more than 180 articles in national and international conferences. So he has also received some research awards and is currently research fellow with the Brazilian Research Council. So I think we changed now from composites to metals, I would say. And I invite you to be with very attention to this new topic. And we have the pleasure to listen now, Professor Ruggieri, please.
The microphone? Okay, it's okay. Okay, thank you very much. Good afternoon to everybody. It's a real pleasure to be here today. I'd like to thank the organizing committee for inviting me. It was a real pleasure to be here and talk about the topic that we discussing with you today. I'm also positively surprised to be so many young faces here to learn more about the field of fracture mechanics. So I understand that this morning you had some lectures about composites, and then we are switching gears and addressing structural steels, metallic materials, which is still a large part of many engineering structures in the world. So I think it's still a very important topic. So this is the outline of my presentation. Just a second. I understand there are two rooms here, so if somebody has a question and they need to approach, please do so. Just raise your hand and probably you approach and see, because we the laser pointer is, as you know, the laser pointer is working only on one side of the screen. Okay, so this is the outline of my presentation. First, I will just present a few cases and discuss fracture as a structural failure limit state. And then I will introduce you with the fundamentals of what we call fitness for service, engineering critical assessment, which are methodologies, engineering methodologies for essentially defect assessment in service structures. Can be used for at the design phase, but they are mainly really applied for the structures which are in operation. Okay, and then I'll give you an overview of the submarine infrastructure for oil and gas offshore production, and then some specifics of the what's over here. No, it's not showing. Okay, never mind. Specifics of ECU procedures for offshore structures, and I'll focus more on the riser and flow line installation, because those are the key components in the offshore subsea infrastructure. And then I will also discuss some key issues in fatigue assessments, which are also important. Before proceeding, I just want to tell you that this is a very vast topic. So probably we won't have time to discuss all the details in 2 hours. This is probably We should have the whole day for discussing all the details. So I'm planning to give you, this is a very extensive presentation. I'm just planning to give you an overview, so you have the fundamental concept, so you can either pursue a more specific investigation, if you like the area, or you have the basis for extending novel applications for offshore structure. Okay, so let's go. First, discuss the fracture structure failure limit. Okay. And the focus really is on cleavage fracture. So it appears that cleavage fracture is outdated. You see a lot of research papers talking about ductile failure, environment-assisted cracking. But in fact, cleavage fracture is one of the most dangerous and spectacular form of material failure. And the important issue is that cleavage fracture often occurs due to small but neglected defects. And you have to understand, all engineering components, structural components, they all have, at a certain point of their operational life, in service life, they will have crack-like defects, all of them. And especially at the weldment. So remember, we are talking metallic materials. So although the focus of the presentation is on steel, but we have other structures made of aluminum, titanium, copper alloys, and so on. So in general, most of these structures need to be welded, and the weldment is usually the weakest link of the structure, and also highly stressed regions. So, despite the advances and increased interest in, as I said, novel materials, including nanoscale alloys, which are a very trend for advanced applications, fusion reactors, high-end applications, for example, aerospace aircraft turbines, cleavage fracture is still a very important failure mode. So we see these happening almost every day, especially in the industry. Okay, and then I would like to show you some of few cases. For example, this is the cleavage. It's a cleavage fracture that occurred in during the hydrostatic pressure test in a pressure vessel. So you can see here. I'm not sure when my mouse is not showing here, but for you guys, I'm going to show the laser pointer here. So you can see here, this is a brand new pressure vessel. During the hydrostatic test, which is a mandatory test after the fabrication, you can see here almost no plastic deformation, which marks or it shows clear cleavage fracture, and probably induced by weld defects and low temperatures. Another case is yeah. No. Okay. So out of the screen. Thank you. Okay. This is a steel mill. So this is how the steel is made. This process. This is the high furnace, and these three guys here, these tallest pressure vessels, they are hot blast stoves. So usually it works like that. Every 8 hours, because you have three, so they work in a shift of 24 hours. One of them is blowing hot air inside the high furnace. So it's the steel is made by the reaction between iron and oxygen. And then in 2002, one of these exploded by actually stress corrosion cracking, initiated stress corrosion cracking, because there's a lot of, especially nitrites, some nasty gases that go back to the stoves, and this contaminated the wall of the vessel. And after a certain time, because of the pressure, this literally exploded. So you can see here, this is the dome. It's a piece of more than 200 tons. Okay, and it's exploded and passed through the belt. This is the transportation belt for the iron, and landed after almost 150 meters. Okay, so I'm not sure if it's clear, but it's you can see the size of this piece. You have seen the engineers are here at the plant looking at the damage. And very common also is a pipeline failure. Here in Europe, especially in the US and in Canada, so the US alone has 500,000 kilometers of pipelines. And it's a very common failure actually. We don't hear a lot about this, but usually it's ductile at the end, but in most cases it begins as a very small cleavage cracking, either by stress corrosion cracking, by even corrosion, localized corrosion, picking corrosion, that eventually will evolve into microscopic crack. Okay, and just to show you the severity of this, I have a movie here, which this is a burst test that is usually performed before the pipe can enter into service. So you let's see, I can. And this is the warning, okay? If it's a natural gas, the damage is much worse because the gas has a very large elastic energy stored. So when there is a leak or when there is a crack in the gas, in a high pressure gas pipeline, the damage is much higher because of the elastic energy stored inside. And finally, I'd like to show you a very recent case. What's the Kobe, the Hanshin earthquake in Japan. Hanshin is the area that connects the Osaka city and Kobe city, which is a port in Japan. In January 17, 1995, about 5 o'clock in the morning, there was a very huge earthquake in the area. Almost 6,000 people died in that earthquake. But the let's say the losses they were very huge losses because of damaged buildings, damaged bridges like this one. This is the bridge that connects the Osaka to the Kobe area. But what's interesting is that one year before, there is a very similar earthquake, about 7.2 in the Richter scale in California. California, as you all know, it's a geological flaw, so it's very prone to earthquakes. But 1 year before, there was a very similar earthquake where the damage was much smaller. And here in Japan, at that time, besides of course the losses of the human lives, the damage was very high. It was very high. And you know, Japan is very famous for their seismic engineering. So how could that happen? And when they did a very thorough investigation about the causes, actually my supervisor was in the investigation committee. This was a few months after the earthquake happened. And they discovered that many failures occurred at the welding between the column and the beam, because this is a very common structure for seismic steel structures. The column and the beam, they are welded together. And one of the aspects, the key aspects of the I'm not sure why my mouse keeps disappearing here. I'm sorry. Okay. The key aspect of this earthquake was the large strength. So the ground motion was very large. Large ground motion implies in large plastic strings, and the plastic strings nucleated brittle cracks at the welding connection. So poor welding. Stress concentration, poor design in the connection details, occurrence of brittle phases or brittle microstructures in the welding. So this led to the occurrence of many structural failures like the ones that I showed here. Okay? So this is just to show you how clipped fracture is still important, because even though we are going toward new materials, new process, new fabrication production. Okay, so of course this was known, the issue of failure by defects, not only defects that remain present in the structure at the beginning at the fabrication, but especially defects that were present during the operation of the structure. So because of this, about let's say 30 years ago, researchers came up with the idea of introducing what you call engineering level methodology. So it's based on fracture mechanics, but it's not very complex. That's why we call engineering level procedure. So it should be rational, it should be simple, and should be effective. And that's the basis of the fitness for service, or also is perhaps better known nowadays, ECA analysis, engineering critical assessment. Okay. Before this, I want to discuss what's the, let's say, general criteria for accepting a structure which has just been fabricated. Okay? This is called workmanship acceptance criteria. So in general, workmanship standards, they provide acceptance criteria for structural components, particularly welded structure, based on good quality levels. It's sort of semi-empirical procedure. Okay, so many codes like like for example, ASME, which is American Society of Mechanical Engineers, especially the ASME code for fabrication of pressure vessels. AWS, which stands for American Welding Society. API is American Petroleum Institute, North American institutes in there. And in Europe here, British Standard and European code. Okay? All of them, they somehow incorporate some acceptance criteria, which is based only on experience most of the time. Okay, so it works like this. If during the fabrication, for example, this is API 1104 for the welding of pipelines and related facilities. So if a crack or a flaw, okay, by the way, there's a difference between a crack and actually a flaw. A flaw, of course, is a crack, but for example, porosities, some volumetric imperfections that may arise during the inspection of the welding, they also can be categorized as flaws. So they are volumetric. For example, they are round. So actually, I am assuming that everybody here took a course on fracture mechanics. So you know the stress fields, linear elastic fracture mechanics, HR, stress fields, J integral. So you need a sharp crack to derive your crack tip stress fields. When the flaw is blunted, so it's round, there is let's say a finite radius. Strictly speaking, we don't call this a crack. But for the workmanship acceptance criteria, they are flaws. So if they found anything which is, let's say, strange, okay, it's not continuous. These flaws should be removed, repaired, and then re-inspected. So, okay. So that's the idea. If you find something strange, you repair it. But this is during the fabrication. It's okay. I mean, it's not very rational because it's kind of arbitrary. But that's okay because it's during the fabrication. Okay. The problem is when the structure is already operating. especially when we talk about welding. As I told you, welds are perhaps they are often the weakest link in a structural component. So think of this, okay? The steel company here in Europe, let's say, I'm not sure, Mannesmann, Vallourec, whatever, they produce a very nice piece of steel, okay? High strength steel. So it's the process is controlled. You have, for example, it's controlled rolling with heat treatment. So usually you stay very close within a very narrow band in temperature. So you have a very fine microstructure. Then you roll the plate, so the microstructure is elongated. So you have very nice properties, mechanical properties and toughness, especially fracture toughness. And then you send this to the shipyard. You send this to the pipe shop, to the plant, and the materials need to be put together. Okay, so it's different than composites that you have in the morning. Which the process is different, and the process of putting the metallic structures together is by welding. In 90% of cases. Okay. In the airplane, you see something different, especially in, let's say, standard airplanes, because the fuselage is made of aluminum. Okay, of course you can weld aluminum. This is a very, let's say, well-known technology nowadays. Nowadays, the welding has improved a lot, okay? Especially with robots and automatic welding. However, welding is still the weakest link. So you don't want to board in an aircraft which is welded, because if a crack develops during the flight, okay, the crack will just run as long as it has material to propagate, and of course enough energy. Okay, this Griffith's principles. If you have, for example, what's the standard way of propagating the airplane fuselage, if you have a rivet, the plates are sort of superimposed. So if a crack develops in one panel, it won't propagate to the other panel. That's one of the reasons why the fuselage is not welded, especially for aluminum. Okay? Of course, I'm not discussing about composites like the new trend. But in most of the structural components, the way we put things together is by welding. Okay? Even in a nuclear reactor, or the pressure vessel in a nuclear reactor, which the most important component in a nuclear power plant is welded. As a matter of fact, the main concern in the nuclear reactor is it's what they call the weld belt around the pressure, and that's because welding is a thermal process. So again, you get in at the shipyard, at the pipe industry, a very piece of steel, of plate, where you made the pipe and then you have to weld it. The thermal process will just make things very different, because you have first a non-controlled thermal process. Of course, everybody here in this room remember the ion-carbon equilibrium diagram. Okay, so we have the transformation, fluoride, then we have austenite. So when it's one cycle, very controlled, so the microstructure transformation is very fine. So if the cooling is very low, all these microstructures are transformed in a very nice way, and when you work at the room temperature, you have very nice microstructure, so you understand very well what's happening, because we of course tested before. With welding is different, because first the cooling is very different. So you melt down a very concentrated piece of metal. Okay, it quickly cools down, so the transformation is very different than the initial, let's say the controlled transformation. But worse than that, after of course, the welding, you need to do many passes. So this is called the root pass. this is the reinforcement, and you have usually 10, 12, depending on the thickness of the plate, you have 10, 12, 15 passes, okay? And either automatic or manual welding. The second pass, the third pass, will reheat, which was already transformed. So you have a very complex, let's say, phase transformation here, and this is very bad. Okay, in many steels, especially because of alloys, niobium, nickel, chromium, they all act as how can I say, preferential points for the solidification of bad stuff. What we call local brittle zones. High islands, especially, that's the name that they keep. High islands of high areas of reaching in high carbon. Okay, so very brittle. That's one of the reasons they usually fracture occurs at the welding. Okay? So the basis for the fracture mechanics phase assessment is this. Again, fracture mechanics has evolved a great deal of knowledge, especially in the 30, 40 last year. So let's use it. So the idea of fitness for service assessment is to use fracture mechanics. And as such, we can use then the applied stresses. So I can have a knowledge of the loading, the actual loading, the remote loading. It's not very easy sometimes, but we can estimate, we can measure, we can quantify the applied stresses. We can also quantify the measured material properties, especially toughness. Okay? The critical value of the J integral, the critical value of the CTLD. I'm sure and I hope that everybody is familiar with these concepts. If not, I will just give you a detail later. To determine, that's very important, to determine what's the tolerable defect, or what's the critical flaw size that can remain the structure without essentially doing nothing. Okay, that's the idea. Remember that workmanship standard or criteria, the philosophy behind was this. If you find anything that looks like a flaw, discontinuity or something like that, okay, you just repair it. Using the ECA philosophy, even if there is a flaw in your structure, you analyze using fracture mechanics constantly and say, okay, this flaw can stay here. I do not need to repair it because it's not critical. Okay, even if there is a flaw, given the applied stresses and given the material properties that I have, essentially toughness, okay, and mechanical properties, fluid properties. So in the past years, I would say the past 20 years, but recently it's even more, has been increasingly adopted and often mandatory. Okay, it's mandatory in many applications. For example, that I'm going to show you is focused on the infrastructure submarine. So in this case, it's mandatory. You must use, otherwise you cannot perform your operation. And they are ideally suited for mechanized welding in combination with automated ultrasonic testing. And this is a very important thing because in the past, the inspection, especially the welding, okay, was made with X-ray. It's the same principle when you go to the doctor and the doctor says, okay, you need to take an X-ray for your yearly checkup, okay? So in the past, that was the standard. So doing, conducting an X-ray for seeing if there are any flaws in the welding, okay? First, X-ray very nice because you see you almost see what's inside the weld. Okay. The problem is it's dangerous. Okay. Performing these, for example, in the shipyard, access to the area in the component. So ultrasound is probably the most widely inspection procedure nowadays used. As you know, the problem with ultrasound is that you are not seeing what's inside the plate or the piece or the component. Okay, everybody knows how it works. It's a matter of emitting a wave and detecting the wave that's reflected. So you have a pattern. You compare your profile of your ultrasound with your pattern. Okay, if your pattern is not calibrated, your reading is totally wrong. One thing. The other thing is, of course, nowadays we have very, very advanced ultrasounds. Okay, ultrasound techniques, very advanced. Phase arrays, even tomography procedures where you can have a 3D scan of your component, but they are restricted to very critical applications, very, let's say, costly applications. In the daily life, the ultrasound has very limited. It is still good, but it has very limited capabilities. So it's very common that the operator, okay, because the guy needs to be qualified to understand the profile. It's very common that the operator misses something. Okay? It's probably like your doctor. Okay? Many of you, or some of you may have heard that some friend or some relative had something and the doctor didn't see it. Okay? And that's because the ultrasound is limited. They have limitations because you're not seeing inside. That's what it is. And because of this, the basic assumption is that, okay, I know that my inspection procedure is not very good. So I'm going to assume that some cracks will remain in the structure. That's the idea. Okay? So for these cases, when I, let's say, put in operation a structural component, okay, I can assume that, okay, my component, I'm going to show you this later, my component has cracks, let's say, 3 millimeter size, because this is probably the sensitivity of my inspection procedure, okay? And then, okay, what's going to happen in the next 10 years, knowing that I have a crack with 3 millimeter size? Because during the 10-year operation, you have fatigue loading, you have thermal loading, because the temperature may change. You have overloading, which is accidental loading. This happens, okay, all the times. I mean, we don't live, please, don't you think that we are living in an ideal world? Okay, this is valid for composite. It's the same. Okay, as soon as the structure starts operating, many things happen which are beyond the design. Beyond the design. Actually, that's in most cases how accident happens. Okay? It's beyond the design. So the design did the best, but in the real world, other things happen. That's life. I cannot say anything else. Okay? And that's the philosophy of the conventional FAD approach. Okay? It's based on a two-parameter curve. It's a very simple, actually, the concept. Okay. Here, in the y-axis, I have what we call. Let me approach this. It's better. Can you? Are you listening to me?
Yeah.
Okay.
Yeah.
Good. If not, please raise your hand. Okay. Okay. The y-axis is what we call the toughness ratio. It's the ratio between the driving force, the crack driving force. I'm assuming that everybody, I'm assuming to a basic course on fracture mechanics, so you all know about crack driving force, okay? And the denominator is the material toughness, okay? So this is the y-axis. And the x-axis is actually the load ratio. It's the relationship between a reference stress, which is associated with a limit load analysis, I'm going to talk a little late, and divided by the yield stress. I mean, we can use the flow stress. The flow stress is usually the average between the ultimate strength and the yield stress. Okay, so there are options of defining the material property, but this is the mechanical property. Okay, the most common is the yield stress, but you can use the flow stress, but most common is the yield stress. And the key assumption is that the failure line, which is this one, okay, does not depend on specimen geometry. It's a very strong assumption. Okay, toughness depends, or I should say, fracture toughness does depend on specimen geometry. And strain hardening. Strain hardening, of course, if you saw composite this morning, of course, you wouldn't be worried about strain hardening. But in metallic materials, we have to worry about strain hardening, which is the, let's say, the regime after yielding. So after yielding, okay, depending on the plastic flow behavior of the material has lower, less hardening or more hardening. Okay? So strain hardening is a very important. Actually, strain hardening is a very important condition, very important. How can I say? Parameter for fracture mechanics. Because when you talk fracture mechanics, necessarily, especially for metallic materials, we are talking about plasticity. There is always plasticity at the crack tip. Always. Okay? Less or more, depending, of course, on the mechanical property of the material. If you are talking about a very high strength steel, very high, 1,200 megapascal, for example, of course, the plasticity is very limited. If we are talking about an ordinary steel, shipbuilding steel, pressure vessel steel, usually is 250, 300 megapascal. Then the amount of plasticity is large. Okay? So the failure line this is a key assumption. So this is more applicable to high constraint conditions, low to moderate ductile materials. Okay, and it's very conservative. That's a very good idea, at least within an engineering sense point of view. Okay, if you are an engineer, for example, in a nuclear power plant, okay, you want to be conservative, even though you know that probably that is the best way of doing things. You want to be conservative, of course. Okay, and this is also very important. This is stress-based approach. Okay, it's entirely based on stress, no strain. And I show you why it's important that we consider also strain. And that's how it works. Okay, if you are when you do your assessment, if you are inside this region below the curve, you are safe. That means your structural component containing a crack won't fail. Okay? If you are outside the curve or the region, this doesn't mean that your component will fail immediately. Okay? Suppose this: you work in a nuclear power plant. Okay? Netflix now has a very interesting movie about the
Three Mile Island.
3,000 mine. That's right. About the movie, about how they didn't tell the story about the problems in the nuclear reactor, and so it's it's a short movie in Netflix. But that's the thing, okay? You do your assessment, and then you find out that your assessment point, okay, is outside the curve. That doesn't mean that the whole thing will just explode and then you need to run to leave your office running. That means that your structure is not safe at that point. okay? And then you need to take measures. That's the idea. And the other nice thing about the failure analysis diagram approach is that actually is a two-parameter. So actually is a combination of fracture, as you all know from the fracture mechanics course, okay? The driving force has to be less than the toughness. And it's a combination, and also the plastic collapse. Because that's the thing. When you have a crack in your structure, think of a pipe. When I give my fracture mechanics course at my school, I always give examples pipes because it's not because I'm particularly fond of pipes, but that's just because it's very easy for students to think about the load. So a pipe, or for example, a longitudinal crack has only the internal pressure of the load, assuming of course it's a long pipe, no bending, no torsion. When you have a crack, okay, think of this. The crack from the fracture mechanics side is intensifying the stresses. That's why we call K, the K parameter as the stress intensity factor, because it's intensifying the stresses, okay? A sharp crack is actually a singularity. On the other hand, when you have a crack also, you are removing material of the pipe thickness. So the stresses, the global stresses, actually the membrane stresses to be more precise, okay? But the membrane stresses, they are increasing because stress is force divided by area. Okay? The internal pressure is the same, so the force is the same. Since you have a crack, the thickness is smaller. If the thickness is smaller, the area is larger. Then, thereby, therefore, the stresses are increasing. Okay? So, in this situation, failure may occur not only or not exclusively by fracture, but can occur by yielding of the what you call the remaining ligament. Okay, so it's a very nice thing that you combine the two failure methods, and you're going to see in a few seconds why this is important. Okay, the other approach is called the CDF approach. It's the crack driving force approach. Okay, which is essentially the same. It's actually in Germany, if I'm not mistaken, GKSS Institute. Okay, they came up with this idea. It's a little simpler, but at the end of the day, it's the same because you need to know the same things, the same material properties, the loading condition. So it's just another way of representing this curve. Okay, but I would say 95% of the cases, the procedures are based on this kind of curve. Okay? And here comes the plasticity interaction. Okay? It's important because the limit load, as I just said, the limit load of the crack component plays an important role in determining its failure, especially in more ductile materials. And this is very important nowadays because nowadays, again, I'm talking about metallic materials, in particular steels. Okay, the steels are getting much better, higher strength, and much higher toughness compared to what we had 20, 30 years ago. And that's what's happening. And the limit load actually is based or is defined from, I'm not going very much into detail, on a limit load analysis. Okay, so after yielding, for example, this is a very, let's say, typical case here. It's a pipe, okay, a tubular specimen under 3-point bending. Okay, this is a very simple problem. In the maximum bending moment, elastic one, it's P force versus the distance between supports divided by 4. Okay, but this is the last one. If you keep applying loads, at a certain moment, you plastify one of the one of the areas here. Okay, you classify, and what's going to happen is actually the moment of inertia will decrease. If the load is if the load is the same, thereby the stresses will increase. So you certainly will pass the yielding in this situation. Okay, at a certain point you will reach instability. This is not fracture. The specimen will not necessarily break. It's like buckling. If you remember of Euler's beam, all that stuff about the critical load, it's like a geometrical imperfection. Okay, when you have the eccentricity, so when you have the applied bending moment bigger than the restoration moment, so the buckling occurs. So it may eventually break, but let's say the cause or the root cause of the failure is actually geometrical. It's not the material. Okay? Here is the material, of course, because it's plastic, but the instability does not necessarily cause fracture. But the structural component loses its capacity of support, of supporting load. Okay? And in the procedure, then we combine all these by standard solutions. For example, this is the API 579. I'm going to talk later. Okay, so the procedures for ECA analysis usually they provide an extensive compendium of reference solutions or limit load solutions for a variety of components with grains. Okay? And that's just to show you the importance. It's a very simple case. Imagine a center cracked panel. Okay, this is a ASTM terminology. It's a middle crack under tension with a center crack. Okay, so if you conduct a very plain, simple fracture mechanics analysis, okay, here are the specimens. The KLC value is the fracture toughness value in the last regime is 200 megapascal square root meter. The yield stress of the material is 400 megapascal, and the applied load is 7 meganewtons. So if you do the calculation, you find out that from the fracture side, okay, your structure is safe. Of course, if you don't consider any safety factor, I just mean that your driving force is less than your toughness. Okay? Of course, in the real world, we would take into account some safety factors for uncertainty, but let's forget about uncertainty. So, okay? So, fracture did not occur, or does not occur. If you consider only the yielding of the ligament, this is the ligament here. If you consider only the yielding, okay, you find out if you do the math here that your applied stresses in the remaining ligament here, okay, is less than the yield stress. Again, forget about the safety factor, but that means that your ligament has not yielded, so your structure is safe. However, when you combine the 2 points, okay, this is the toughness ratio, and this is the load ratio. What happens? Your point falls outside the curve, and that shows that you are in a potentially unsafe region. So you should look at these in more detail. Okay? But this is how to show you the importance of combining fracture and plastic collapse. Okay, I'll go a little briefly over these because you really, again, I told you we should stay here. I know you don't want this because it's a very nice day outside. Okay, but we'll be here all day long, so we could go into details of the procedures. I should perhaps not say this, but I have the procedures. Okay, of course we cannot distribute publicly, But if you ever need the procedure, so you either talk to me or talk to Professor Luis Hayes, and probably I can send you an email. I have access of this because I work with the Brazilian state oil company, so actually I do a lot of projects with them, so actually I have access to these documents, okay? So you just send me an email and we will send you a copy. As long as you promise you are not going to distribute this to your colleagues, okay? So, but anyway, again, as I told you, the idea is to produce a fractal mechanics based methodology, okay? But in a simple fashion. So engineers, of course I'm not saying that engineers are not capable of doing mathematics, but just saying that in the real world, sometimes you need very quick solution, okay? In a very simple procedure. So most of the procedures are the let's say, the most widely used. There are others, okay, in a minor scale. This is the so-called R6, which actually is the first one, okay? I say this is the mother of all procedures. So this was introduced, I think the 80s, probably, okay, by the UK Nuclear Generating Board. So actually this was a procedure introduced by the British in the 80s, okay, to deal with issues for the nuclear industry. The procedure turned out to be so good in terms of simplicity and robustness, effectiveness, and so, okay, that others that came after started building similar procedures, of course, suiting their needs, but based on the R6 procedure. And nowadays, actually, is who actually manages all the updates and the distribution is EDF, the French EDF Energy. Okay? The other one which is widely used in the oil and gas industry, okay, is the British Standard 7910. And the most recent, and probably one of the best ones, is API 579. It's a very comprehensive, because it has many solutions. I'm going to show you. Okay? The other one is the SynTech, which was developed during the 1995 European Union, all countries were, okay? The British still didn't think about Brexit, so everything was in peace. So they came up with this, let's say, European Union procedure, okay? And this is freely available, the SynTech, okay? The thing is, it's a good procedure, okay? But nowadays nobody uses, so that's the problem. So for industry, from let's say an industrial perspective, just people don't use it. Okay, but it's a very good procedure. And the last one is the TITNet, which is an recent effort between also some countries in Europe. I don't remember who. UK, Germany, Spain, France, Belgium, some others. So I'm sorry. If I don't say all of them. Also to complement all the procedures. Because the thing with this procedure is, they are all good, but they are not the same. One procedure can address a specific case, and the other procedure can address another specific case. So that's why I told you that if we are going to address this in detail, we shouldn't stay here probably all day long, because then you need to compare what's the response of one procedure in comparison to other procedures. I'm just going to give you an overview so you will have, you can conduct your research on your own. Okay? So, but what's common to all methods is that they cover the whole range from linear to elastic class behavior. Okay? Some different routes, correct driving force solution, and other assumptions. Okay? So, the British Standard 7910, as I told you, is the standard in the oil and gas industry, as well as in many other industries. Okay? For some reasons which are beyond the scope of this course, the British Standard was very good at marketing their code. So that's why they were very successful within the industry. Okay, they have many sections, but the ECA basic procedure is based on this here. Okay, we have level 1, 2, and 3. And by the way, this is another very good thing about all these procedures, is the level of assessment. Actually, I think this philosophy should be employed everywhere. Okay, they work like this. I detect during inspection that my structural component has a defect, a crack-like defect. Okay. Okay. In the real world, not always we know the load with details. In the real world, not always, actually it's more common than you think, we know the mechanical properties of the material. Think of this, okay? Think of your city, your country. You have a pipeline, a gas pipeline, that's running that has been operating for the last 30 years. So it was fabricated 30 years ago. Do you think that they keep track of the records of material testing, mechanical? No. No. I mean, in many cases, no. And that's the real world. So when we have to conduct an assessment, especially in old structures, vintage structures, we have to estimate the properties. We have to estimate the loading. Okay? And then that means that we have to be very conservative because there are many uncertainties. So the levels inside the methodology takes into account the uncertainties and the conservatism. For example, if I know nothing about the material. I have a very, let's say, dark idea, gray idea about my loading. Level 1 will give you a very simple assessment and very conservative. That's the idea. Okay? Then there are two possible scenarios here. Suppose you have a crack, you did the assessment, and your crack is acceptable for level 1. Well, if your analysis was very conservative, then we are okay, because we know we're very conservative. Okay? But suppose this scenario, your defect is not acceptable per level 1. Okay? Then, because we know that I was conservative, we can move to the next level. The next level requires more details on loading, more details on material properties. Okay? Then the level 2 is less conservative. That's the idea. Okay? Again, as I told you, doesn't mean that when you don't accept a crack or a defect, that doesn't mean that you should just leave your office and run away because the whole thing works for no. Okay? You can go up the levels until, of course, you let's say exhaust your analysis. That is the standard level 2A. Okay? Level 2A, let's say, is the standard route. Okay? We have many. Because of time, I won't go into details here, but there are many options here. Again, you really need to practice this. Okay?
May I suggest you something?
Okay.
You can define the point which are going to safe zone or unsafe zone.
Okay.
But how do you define the curve?
No, the curve is predefined. This curve here, which KR is a function square to the other, this is defined.
Not this curve. Actually, safe zone curve. How do you
The
define?
safe zone is unsafe. If you're inside, you are safe. Was that what was?
Actually, you were using some graph that shows
Yeah.
that stress integrity curve, stress integrity ratio, and versus
Okay.
stress versus, and you draw a curve like this one.
I think I think it's this. You mean the load path?
Yeah.
Okay, I'll go back. No, it's here. Here.
Yes.
The load path.
Yes.
Okay, the load path, this curve. Which way you go? Okay, this curve. That curve is predefined. Okay, the loading path. This is your calculation. You need to calculate, for example, for the internal pressure, the pipe with internal pressure. You have the internal pressure. Okay, and then you calculate your driving force, and you calculate your load ratio. If the internal pressure increases, you are going up. If your crack size increases, you are going up. So this is, let's say, input data. Okay?
What we understood is it's a corrective stress showing. Load path means corrective stress.
Here. Okay? Where is my mouse? The mouse is not showing up. Okay. I'm not sure why the mouse is not showing up. Okay. Some aqui. Aqui, ó. Então, mas não aparece. Aqui, ó. Então, aqui, ó. Cadê? Oh, here. This is your calculation. You have the applied stresses, then you have the driving force. Okay? You know the material properties. So you have the toughness ratio. And here the same. You have the stresses, you know your reference stress. Okay? So this is input data. The stresses and material properties. Okay? The loading path, because of this, if you have a single internal pressure and a single crack size, you have 1 point here. Okay? However, if the pressure keeps increasing or the crack size keeps increasing for some reason, then you probably are going to follow this. Okay? Okay, where were we? Here. Okay. So this is the standard procedure. The bridge standard has up to 2 sub-levels, okay? 2A and 2B. 2B requires the stress strain curve, so actually it's more precise. Okay? And that's the validation here. This is just a validation. This is from the work of Christopher Lizard. You can see here. So actually, the validation just supports the curve. This curve is a sort of semi-empirical, so it's not an actual mathematical derivation. So we start from the corrective stress fields, from the reference solution. Okay? It's the envelope of the lower bounds of the experiments. Okay? Level 3 is an advanced procedure. As I told you, as we increase the level, okay, the analysis is more accurate. It's good, but then I need more data. I need more data, more experimental data, more knowledge about the loading. And also, level 3 enables using a ductile tearing analysis. Okay? Because again, in the real world, when you find a crack, the crack does not always stay at the same place, the same size, static. Okay? The the crack size can increase because of further loading. And I'm not talking about fatigue cycling. It's just because of overloading. Okay, the stress can increase in size. If the crack can increase in size. If the crack increases in size, I can take this into account. Okay, by including a ductile theory analysis of stable crack growth in the defect. Again, the procedure has many details, but and you have just to follow the procedure. But it's essentially like this. You need a resistance curve, an R curve, J resistance curve, and as the crack is increasing, your assessment point is also moving. Okay, and then you do your assessment depending on your expected ductile tear. API 579, okay, again, it's from the American Petroleum Institute. This was the first edition was in 2000, so it's a new procedure. And it's a very, I would say, it's a very comprehensive procedure. So the fundamentals are the same, okay? Fundamentals are the same, you can see here. The curve is the same. The difference between API 579 and British Standard 7910 is the solutions for the stress intensity factors. Okay? The stress intensity factor solutions incorporated in British Standard level 3, British Standard procedure, okay, relies on a very simple computational, it's a very simple calculation of the stress intensity factor for curved pipes, for example. Okay? So we usually get an analytical solution for a flat plate and just considers the curvature. Okay? Therefore, it's an approximate solution. It's a good solution, it's approximate. API 579, all the solutions incorporated into the code, into the procedure, are based on finite element analysis. So they are very accurate, very. Okay? And this is important because, for example, in some cases, the difference between the stress intensity solution, the difference of the stress between the stress intensity solution for the API 579 and British Standard is something like 30%. Okay? So it's a lot. 30% is a lot. Okay? But nevertheless, the oil and gas industry most often uses British Standard for reasons that are beyond the scope of this course. Okay? Okay. And the other thing that you need to consider when dealing with this defect assessment methodology is the stress classification. And that's because this is a general view. Of course, there are a little bit more details, but let's say 90% comes to this. You have either primary stresses and secondary stresses. Primary stresses are loading. For example, this is an example of a pipe with a longitudinal crack. Okay? The primary stresses are the stresses coming from the internal pressure. That's the load. Okay? The secondary stresses are, most of the cases, associated with residual stresses. Again, we are talking about metallic materials and steel structures that are all welded. So besides all the problems with brittle zones in the welding, in the heat effect zone, etc., we also have residual stresses because of the thermal cycles. Okay? And in some cases, for example, nuclear applications, of course, everything is stress relieved. Okay? Because that's why a nuclear power plant costs millions of euros or millions of US dollars. Because it's very expensive to build. But in many cases, for example, in the petrochemical industry, you are not going to stress relieve all components. Okay? So we have residual stresses. And residual stresses are important because residual stresses act on the driving force, on the crack driving force. Okay? So that's why most of the methodologies, they have different ways, but they have a form, a way of correcting the driving force for the residual stress or secondary stress. Okay. What else here? Okay, that's probably the actual picture. Okay. I think that will also answer further your question. Okay. Here is the true API 579 level 2, the curve. Okay. So this is the operating point. You calculate here. So again, the internal pressure vessel. You have the internal pressure. You know the membrane stresses. Okay. And then you get your stress intensity factor solution, and then calculate your driving force. Okay? And the next step, you either evaluate in the lab or you estimate your fracture toughness. So you divide the driving force. You divide the driving force by the toughness, and then you have the toughness ratio. Let's say it's 0.6. Okay, and then you go to the load ratio. Again, you have the internal pressures, you have the membrane stresses, circumferential stresses, PR over T for thin wall pipelines. Then you go to the code, and you get your reference solution. Then you get sigma ref. You know the yield stress of the material, and then you divide the reference stress by the yield stress. Then you have your other point here. Okay. So the intersection of these 2 points defines the operating point. It's as simple as that. Okay? If it's below the curve, it's safe. If it's outside the curve, it's not safe. Then you need to take measures. Either, for example, in this very simple example that I just gave you can, and that's very common. In the petrochemical industry, this is very common because somebody finds a crack in a, let's say, heat exchanger, pressure vessel, and the petrochemical industry cannot stop. Okay, those guys, they work 24/7, 7 days a week, 24 hours, cannot stop. Okay, unless it's a, let's say, scheduled maintenance. And if they find a crack and they do the assessment, it's something like a little bit unsafe. What they do is they reduce the pressure. That's the easiest way. Okay, they just reduce the pressure and keep moving. Okay, that's another way of showing this. Right? Okay, as you can imagine, if you are in this side of the curve, that means the material is brittle. Okay, because your Kr is close to 1. That means the material is brittle. And if you are in this side of the curve, here, that means that your material has very high toughness. So the failure is controlled by yielding, not by fracture.
There is something I don't understand here, is that if we are at the very right of the FAE, so it's a
Here.
general yielding.
Now here is yielding.
On the right, yes. Then the K factor doesn't mean anything normally, because you can only apply the stress intensity factor if you have limited plasticity.
Very good question. Very good question. Okay. Actually, the procedure, since it's very conservative, okay, it ignores the so-called size requirements for K control. So you are familiar with ASTM E399, very severe conditions for ensuring that this is linear elastic. Okay, this ignores it. Okay, it's a very good question because it's supposed to be conservative. Okay, then this, for example, suppose you do your ASTM E399. Okay, are you familiar with it? Okay, but you have the requirements. Okay, so for example, here is this 2.5 times, for instance. Okay, K1C divided by yield stress to the square.
Yeah, it's like the 14 times.
Yes. Yeah. So, for example, okay, because I give this example all the time to my students. For example, if you have a material with a critical stress intensity factor, critical stress intensity factor of 100 megapascal square meter, it's a very typical value for steels. And your yield stress is 400 megapascal, which is also a pressure vessel steel. For example, a nuclear pressure vessel steel has 400, 450. Your specimen size to obtain a valid K1C per ASTM 399 is 120 millimeter thick. Okay? So your specimen has this size. No, that's true. That's true. Okay? And then that's why and then you go to your assessment. Your pressure vessel has 20 millimeters. Okay? And you say, gosh, how can I calculate the driving force if it's 20 millimeters? Well, because this is supposed to be conservative. Okay? That's why, if in this case that we just mentioned, your assessment is unsafe, that's why you can move to the next step, because then you're going to calculate J, not K. Okay? Okay? You got the point, that's why. But usually when your crack is acceptable in the per level 2, we're fine. Because you use a very conservative assessment. Okay? Okay, just to summarize again, if we may or Professor Reis, I can send you the code so you can look inside. Okay. Also in the reference, I put more references or details on the methodologies. It's just an overview, but it covers let's say the fundamental philosophy. And because of the conservatism and the simplicity, that they have emerged as one of the most effective, versatile, and yet robust fracture mechanics-based methodology. Because even though it's conservative, we are still using fracture mechanics. Okay? We are not using any empirical observation, any guessing. It's based on fracture mechanics. So I know the driving forces, and I know more details. And largely adopted in several critical structure applications, as I'm going to show you just right now, especially for in the offshore. Okay, but they still need a lot of improvement. So of course, I don't want to show myself as a car salesman. You go to buy a used car, and the car is perfect. When you turn right down the road, so the car just falls apart. Okay. Of course, it's a very good procedure, but it needs improvement, especially for the new generation of materials that's coming. Okay, it works very well for pressure vessels, standard applications. And then we are going to extend this to the offshore oil and gas infrastructure. Okay? There is a mistake there. Sorry. First of all, I'd like to give you bad news. Okay? So, despite all of this talking about renewable energy, solar energy, wind, which, by the way, I am totally in favor. Okay? I hate to show you this plot. I hate to show you this plot. But the truth is, first, we cannot just turn off everything. Renewable energy will not be capable of replacing fossil fuels in the short term. That's unfortunate, right? That's how it is. So, and probably this is going to get worse with the conflict here in your garden in the Ukraine because of the supply of gas and other resources. And because of this, this comes from the British Petroleum Energy Outlook. It's a very good. If you need to have any estimate, you are drafting a proposal or something like that, you need to have a look on the energy outlook for the next 20 years. That's the way. That's the place to go. The British Petroleum Energy Outlook. There are others. Even the International Agency of Energy has very nice outlooks, but that's a very good one. And as you can see here, at least until 2035, 2040, we are going to see an expansion of fossil fuels exploration. especially natural gas. Okay, unfortunately, I hate to say that, but and because of this, the oil and gas exploration is going farther and deeper. Okay, this is just to show you what's the geological profile. So usually the oil and gas is very deep geological formation. Okay. And because of this, okay, the technological challenge in pipeline and riser design, for those who are not familiar, I'll just define in a moment which is a riser, okay? Installation, operation, inspection, and repair. So the technological challenges are enormous because the loading conditions, the high strength steels, high strength materials that are needed in many aspects. Okay? And this is the typical scenario of the offshore and subsea systems. Okay, so this is past. Okay, this is shallow water. What you call shallow is 300 meters. 300 meters shallow. So this is a piece of cake. We are talking about exploration and drilling in 1,000 water depth. 2,000 in Brazil, we at least I think the record now is the Gulf of Mexico, but I think 2 years ago the record of deep water exploration was in Brazil. Was almost 2,500 meters water depth. This is the water, okay? And below this, you still have more 5,000 meters until you reach the reservoir, okay? And then you can imagine all the infrastructure that goes subsea. I mean, we don't see that, but okay? And particularly because, for example, onshore, okay? You see on those movies, those cowboys movies on TV, okay? You see a lot of pumps, pumping wells, okay? And onshore is very cheap. So we can put a lot of pumps every 100 meters or something. In the water, this is not like that, because it's very expensive. It's very expensive to construct and to operate one of these floating structures. So what's happening is one floating structure usually has many pipes and many connections to many wells. So there is a very sophisticated, let's say, infrastructure on seabed. Okay, like this, for example. This is a template, has many valves, many connections, many flanges, many everything. Okay, and all of this. Oh, and this is also, it's not shown here. Oh, it's shown here. This is also. My mouse is tricky. Called FPSO technology. So because this is very expensive to build, and also in some cases, like for example in Brazil, because we have to speed up the production. Okay, usually what Petrobras, which is a Brazilian state oil company, what they usually do is that they transform large ships into platform oil production. So it works like this. You have here the drilling, and all the pipes go to the seabed, and then when the oil is coming, they store some part of the oil in here, and that's why this stands for. This is float production, storage, offloading. Because every 2 weeks, every 1 week, I'm not sure, but every some time, okay, another ship comes and then offloads the oil and then goes to the to the land, to refinery. Okay, and in this scenario, the subsea pipeline infrastructure is probably the most important infrastructure in this. Okay, so here is a semi-submersible platform. You can see here all the array of pipelines here. Okay, you can see they are together, and they are steel, metallic, usually steel pipes. Okay. And the most common way of installing these pipes is by drilling. So believe it or not, this is a 18-inch, let's see, this is about 300 millimeter diameter steel pipe, okay, which is reeled in a very large drum. It's reeled, then it's unreeled and then installed on the seabed. Okay, so what do we have to do with this? Is because this imposes a very challenging assessment during the installation. Actually, you can see here, the girth weld just broke apart, okay, because of the high strains, high stresses, and the plasticity. Because this is the deformation here is in the order of 3% below BPU. Okay, that's a lot of strength. And those are the challenges that we have. Okay? High stresses, larger thickness, water depth exceeding 1,000 meters, and also sour tuning. This is also a nightmare. Okay? Because the oil comes with many things. Okay? You don't just open the valve and just oil comes. Oil comes in brute form and just take it to the refinery. It doesn't work like that. There are many things, including salt water, very salty, that you need to separate. Okay, but as far as fracture mechanics is concerned, one of the problems, one of the headaches is H2S. It's very corrosive, and also CO2, which is carbon dioxide. So the carbon dioxide, which is inside the reservoir, they combine with water and then produce carbonic acid. Okay? And one particular change that we are having now is we are going even deeper, because the large reservoirs that were found about 10 years ago, it's underneath the salt layer. So that's called the pre-salt reservoir. Okay? So you have the rock, the geological rock, and then you have a salt layer, and then you have the oil reservoir. Okay? So all of this will cause many problems. For example, this one. Okay? This is a flexible pipe. It's not a rigid pipe. It's a flexible, but the principle is the same. Okay? Inside the inner layer is a sort of composite, okay? Polymer, the inner pipe. But of course, the polymer cannot resist 1,000 water pressure. Okay? Then you have to do a very sophisticated arrangement here with what you call armor, a tensile armor, which is made of high strength steel, 1,000 megapascal instruments. We are just testing, folks. We are just testing these steels in my lab right now. And the CO2 that comes with the oil and gas somehow goes through the polymer and reaches the steel. And then you can see it. Okay? This can be a very nasty accident with very potential. Unfortunately, it didn't happen. Potentially large catastrophic environmental problems. Okay? If this really brings. Okay? And because of this, the new generation of pipes actually is lined inside with a very expensive Inconel layer. Nickel, chromium, is not standard stainless steel, 316, 305, okay? It's Inconel 625. With high nickel, high chromium, very expensive, and because it's very expensive, usually what we do is the outside pipe, which should resist the pressure, is standard pipeline steel, X60, X70, okay? And the inner side is usually is a 3 millimeter layer of Inconel 625. It's very expensive. However, the pipe in itself is fine. Okay? There are many technologies of Inconel. Lined Inconel pipes is a German-based company. I think it's a boutique or something like that. Okay. But the problem here is the welding. I told you, welding is the weakest link in any structural component. Because this is an inconel layer, the welding is also inconel. Okay? So believe it or not, it's a very expensive procedure. They made a truly dissimilar welding. It's truly dissimilar. So it's inconel and the outside is base weld. Okay? And there are several issues that we're going to address. First, dissimilar girth weld. Okay? When you have two dissimilar materials, if you remember your fracture mechanics course, okay? Think of the CTLD or J integral. Okay? In the CTLD for the every models, the opening of the crack is symmetrical. Okay? And then you can even relate the CTLD of the J. Okay? But everything is symmetrical. So when you have the similar material, on top of having all those problems that I just mentioned, that I mentioned before, about the thermal cycle, the microstructure transformation, which is not the same as the base plate material, then we have the asymmetrical opening. Okay? So that makes the assessment of the behavior more complex, because actually we are not sure which CTLD controls fracture. Okay? Is the CTLD in the weaker material, which opens more, or it's the CTLD in the stronger material? Okay? And the similar girth also has an effect on the ECA methodology. Okay? As you can see here in a very simplified way. What's my mouse? Okay? We can see here, this is a simplified representation of the critical CTLD normalized by the crack size and the yield strain, and here is the remote strain normalized by the yield strain. Okay? You can see here that if you have overmatch or undermatch, you are moving your, let's say, design curve to the left or to the right. Okay? What's overmatch? In general, the welding is stronger than the base plate material. This is almost always. Okay? And the procedure is made to produce an overmatch weld. This is common. And the reason is, since the welding or the weld is the weakest link, okay? So I'm going to produce, that was the idea. I'm going to produce a weld which is stronger than the base plate. This is overmatch, okay? But with this new generation of materials, for example, in the pipeline area, since the strength is increasing, okay, the hardening behavior is also decreasing, and the inconel does not have such a high strength. So usually when we have the similar weld made of inconel and X80, X70, in many cases you are going to have undermatch, or at least what it's called partial undermatch. So it's undermatch at the beginning, and then because of the difference in stress strain behavior, so the curve starts to deviate apart. Okay, that's a problem. That makes the behavior more complex. Okay, I'm just going quickly on the specifics. Okay, again, girth welds are subject to large axial straining during installation, and because of this, the tolerance is reduced compared to conventional piping components. Okay, and to a certain extent, internal pressure. But this is something that I have not talked about, biaxial loading. Okay, when the pipe is operating on the seafloor, okay, you have bending. You may have bending because of the ground motion, but you have also internal pressure. because of course the pipe is operating. And we don't know very well, still today, okay, till now, we don't know very well how to deal with the coupling of the driving force and the material toughness when you have biaxial loading. Okay? The fractal behavior is different under biaxial loading than under uniaxial loading. And that's what I'm talking about. Okay? Those are the three basic ways of launching a pipe. This is the S lay, the very common, okay, usually for shallow waters. This is the J lay, okay. So here the pipe is welded. By the way, the pipe is welded. In these two cases, the pipe is welded on board. Okay. It's very different because you have to weld and launch, and that's one of the main reasons for using ECA analysis, because it's a very fast operation. You don't have time to do a very thorough screening, and you don't have much time to do repairing as well. Okay? Because again, the barge is shaking, the weather may be changing, and then you have to move. It's a very difficult. It's not very easy. Okay? The J-lay, the weld the pipe is welded in the vertical position. Okay? That's the only difference. And the relay, or the reeling, the real advantage, the real advantage is that you weld all this line onshore. So it's a very nice controlled welding, covered against the weather. You can repair very easily, more easily. You can inspect more easily. That's the idea. Then you weld onshore, you reel it, and then you move it. But at the expense of introducing much larger loading on the girth wells. Okay? Other problems. So these are the problems affecting flood tolerance. Okay? Misalignment. Again, the real world. Don't expect that the girth wells will be perfect, because they are not. Okay? Residual stresses, strength mismatch, which I just talked about, lateral buckling, okay? And strain-based situations. So the misalignment, which is also called in the area, okay, as high-low. That's high-low is just a term that they use for describing or defining the difference between the pipe that's coming and the pipe that is leaving. Okay, and this obviously this will increase, this will decrease the fatigue life because you have stress concentration just caused by the misalignment. The misalignment actually induces a bending moment, which is superposed on the normal loading. Okay, buckling, very common. That's because it's a very long line. Okay. In many projects, of course, they install some special configurations to absorb the compression loading. But in general, this occurs essentially because of temperature. The oil that's coming from the well is hot, okay? And the water is cold. So, depending on the configuration of the installation, this expansion because of temperature induces compressive loading. So these things they happen. Okay? And these will, again, from the fracture mechanics perspective, these will introduce more complexity. Because if there is a defect in here, okay, you have a bending load which is superposed on the, let's say, normal load. Okay? And strain-based design. As I mentioned before, the fundamental AC analysis is stress-based design. However, with these new generation high-strength materials, that's what's happening here. Okay, this is a low-grade pipeline steel X60. Okay, API. I'm sorry if I have to refer to American standards, but the thing is, in the oil and gas industry, American standards dominate the industry, so there's nothing I can do about it. So I'm sorry. Okay. Of course, the European has some, let's say, counterpart standards, but the prevailing standards in the area, in the sector, is really American standard. So I apologize, but that's the real world. So this is an API X60. Okay, you see here it's a high hardening material, and this is the new generation of high strength steels, X100. So X60 is the yield stress is 60 KSI. Again, these are American units, okay? So kilopounds per square inch, which is roughly 400 megapascal, okay? And X100 is 100 KSI. It's more or less 680, 700 megapascal yield stress, so it's much higher. And because the yield stress is much higher, the behavior, the hardening behavior is different. Okay? That's almost always happen with metallic materials, particularly steels. If you increase the yield stress, the behavior is low. Like this. See? Here. You reach the yield point and the stresses keep increasing because of hardening. Okay? Hardening is nothing more than pile up of defects, okay, that restricts the mobility. I'm not going to detail this. Some of you may be material scientists, you know much better than me. Okay? And that's it. That is. So for high strength steel, so the mobility is lower. So what happens is, after you reach the yield point, you deform the material with much less stress. Okay? That's the meaning of hardening from the mechanics, from the fracture mechanics perspective. Okay? We're not interested in what happens as the leg structure. If it's pile up of any kind of defects, doesn't matter. What matters is that the hardening, the flow, the plastic flow behavior will impact the fracture mechanics assessment. Okay? So this is one thing, and that's why for this class of new materials we should be using strain-based assessment, not stress-based assessment. Okay? So usually, and here it shows the whole story here. Okay? This is J. This is for a center cracked panel. Okay? I'm not sure which material it is because I just took from this paper here. So they didn't mention which material it is, but I guess it's let's say medium strength material. Okay? You can see here. This is the J versus strength. If you use grid standard 7910 to estimate the J value, the J integral, okay, you have this solid curve. If you conduct a finite element analysis, nonlinear, large strain deformation, blah blah blah, all that stuff that you know, okay, you are going to have a different relationship between J and strain. Okay, and that's very important for the assessment. So the general defect assessment procedure here, again, here we're showing the cycles. Okay. Of course, it's not fatigue. Okay. We don't use fatigue, but if you think of, let's say, sort of fatigue, you have 3 or 4 cycles. So I would say it's very low cycle, high stress fatigue. Okay? But I usually don't consider this. That is, we just take the cycles here, actually to estimate the loading. Okay? But what happens is, that's what happens. That's why you don't care about fatigue. What really happens is, suppose you have a defect in the girth weld. Okay? And then suppose that you reel one cycle, unreel another cycle, and then go through the liner here. You are imposing the crack with a very high load. So if the remaining crack was 3 millimeters, okay, by the time you impose the first cycle, most likely the crack extended by another 1 millimeter. So after the first cycle, actually your crack has 4 millimeter. And then you do another cycle when you are going to finally launch. Okay? And you do another cycle, so your 4 millimeter, assuming that of course you have the resistance curve, your crack extended by another 1 millimeter. So actually when you are launching the pipe, okay, your crack actually has 5 millimeter. Okay? And then somebody is going to ask, well, why don't you repair when you can't? There is no way. Of course it's possible. It's possible with nowadays technology. You send remote operate vehicles, some robots, but that's very expensive and very difficult. So the engineering standard procedure is you don't do anything once the pipe is on the seabed, period. And it's going to stay there for another 20 years. That's why you need to do a reverse engineering. That's the way they do, okay? They do like this, okay, I need to be safe after 20 years. So I do all the calculation using all this advanced level of analysis, do all the calculation, and say, okay, to be safe after 20 years operating, okay, but don't be fooled by the picture. There are lots of loads on the seabed, okay? The current, the soil is moving, okay? So you have some, and also you have some loading, fatigue loading, okay? Not high loading on the seabed, nevertheless, some fatigue loading. So you need to be sure that after 20 years, your installation is safe. Okay, and say, okay, to be safe, the maximum crack size is 7 millimeter. Then I say, okay, what's the fatigue loading? What's all the damage that can occur during the 20 years? During these 20 years, I say 2 millimeters. So I subtract. So I say, okay, when I install my pipe, the maximum crack must be 5 millimeters. Okay? And then there's the installation process. The installation process, as I just mentioned, is very simple. Is 1 millimeter by cycle. So 5 minus 2 is 3 millimeter. Okay? So, of course, there is more details than this, but the overall is this. You do a reverse engineering, and then say, okay, the maximum crack size that I can leave in my pipe before launching is 3 millimeters. Okay? That's how it's done. And then this DNV, okay, so I just mentioned American Petroleum Institute, but for the oil and gas industry, offshore, okay, the standard is DNV, which the Norwegian society, which recently, I think was 2013 or 14, I don't remember, the DNV merged with the German Lloyd. Okay, so they have now the DNV GL, and this is the most, let's say, widely, which is the F108. So DNV 108 will give you all the routes, the details to conduct a fitness for service analysis, ECA analysis for launching pipelines. Okay, it's all in there. So here is just a summary. So it's a very detailed, but nevertheless, it's not plug and play. Again, okay, this is advanced analysis. So you need many details, many data. And one of these data is the use of SCP scans. By the way, we are a little delayed. No, how much?
Okay.
Are you fine? Well, I'm fine. I'm just worried that the...
I think we have time until 6 p.m.
Oh,
Or 5-10 minutes. 5-10 minutes.
I like to give hard time to my students. Oh, it's the best part of the class is to give them a hard
It's
time.
more 5-10 minutes.
Okay? I'm teaching 2 courses this semester. One is undergrad. Undergrad is standard engineering course, okay? Postgraduate course. And I just gave them a very, very hard test. The students were, and I just left here, they were freaking out because I said, no, you need to give us another chance. No, you're not studying hard, that's the problem. Okay, but now it's going to be a little faster. Okay, one of the key ingredients in the DNV F18, which is the basis. This is the basis for any installation. Okay, any oil company in the world uses this for installation by grid. Any of them. Okay, is the use of SCP specimens in practical settings. By the way, here in Europe, you call these SANT, which is single edge notched tension specimen. Okay, I'm not picky about terminology. Okay, this is ASTM terminology. ASTM, that's because I remember ASTM, of course, then I will have to use the terminology. So the committee E08, okay, has normalized the terminology for fracture mechanics. And it works like this. The first two letters stand for the geometry. So SE is single edge. The letter that's in the parentheses is the loading mode. So for example, a 3-point bending specimen, which here, I mean, especially in the UK, because that's come from the UK, they call SEM. That's single edge notch bend specimen. Okay, that's fine. We're not thinking about this. But in the ASTM terminology, it would be SEB. So single edge under bending. And why this is important? Because if you have the same geometry, 3-point single edge, the fracture behavior changes dramatically if you change the loading mode from bending to tension. Just by taking that, I'm not changing anything. The material is the same, the geometry is the same. The drawing that you send up to your machine shop is the same. Okay? The only difference is that instead of applying a bending load, like the 3-point bending, you're applying a tension load. Changes dramatically, as I'm going to show. And this is generally called constraint effects. Okay? I'm not sure if you are familiar with the. Doesn't show me. It's very interesting. Okay. On your right, this is the JQ trajectory. Okay. Are you familiar with the JQ methodology? 2-parameter description of crack tip stress fields. Okay. I think this is a no, so probably okay, no problem. When you use J or CTLD to characterize your fracture behavior, what are you actually saying is, okay, if you have a J value of, let's say, 50, okay, 50 kilojoules by, or megapascal millimeter, okay, that means that implicitly you are defining the crack tip stress fields. And then you say, okay, when I say that the J integral that describes the fracture, the express fracture is 50, I'm actually saying that I know implicitly, okay, the stress fields which are driving fracture. That's how it works. Okay? You are not measuring, but implicitly you are actually defining the stresses that control fracture. This works very well. This is we call single parameter fracture mechanics, because you use only one parameter: K, linear elastic, and J and CTLD for elastic plastic. This is one parameter. Okay. And when the plasticity, plastic deformation spreads out larger than a certain amount, I'm going to show you, the correlation, okay, that's what it is, okay, single parameter. It's a correlation between J and the stress fields. When you have more plasticity than design, okay, this correlation breaks down. Okay? So J does not describe anymore the stress field. Therefore, I need a second parameter. It's a very nice area, by the way. Okay? I need a second parameter. This is called multi-parameter fractal mechanics. The second parameter most widely used, there are 3 or 4 second parameters. But the second parameter most widely used is the Q parameter. So it describes essentially the difference between the reference solution and the stress field in your actual practical life. And why this is important? Because this measure the what we call the constraint, the effects of constraint. Okay? So look at the picture at on your right. Okay? So it's J versus Q, because Q is negative. Usually we plot J versus minus Q, just to be more elegant. Okay? But K is negative because it's the difference here. Okay. You see here the CT specimen, is the compact tension specimen. The compact tension specimen probably is the oldest specimen in fractal mechanics. If you go back to the 70s, the beginning of fractal mechanics, especially in the US, all that ASTM papers, Jim Rice, many others. You see a lot of experiments and analysis on the CT specimen. So the compact is the largest used geometry in fractal mechanics. And that's because it has high constraint. Okay? It provides very severe fractal toughness. That's why it's largely used. It's very conservative. Look at the pipe. You see, the JQ trajectory is far away from the CT. That means that the pipe is much less severe than the CT specimen. What's the meaning of this? Again, close to your question. If I use a CT specimen to design the launching of my pipeline, okay, I'm going to be very, very conservative. Very. And the problem here is not a matter of being conservative. The problem is you are doing this on a ship. Okay? You don't have time to do all the repairing. Okay? It's like those movies when you are in a space station and there is something broken outside and the guy goes down there. Okay, George Clooney, there's a film I think George Clooney, that he goes there and the oxygen is going down and he has few minutes to fix the thing. It's something like that, because on a ship you don't have time, resources, and sometimes how can I say, the costs are very high also. Okay? So that's why a very bad idea is to use the SCT, because you see here the curves of the SCT are much closer to the curve of the pipe. Okay? So the SCT is the standard nowadays for evaluating fractal toughness properties for pipelines. And actually, it's so good that other areas are starting to use this, okay, because it's less severe than the CT. Here is a comparison here. You can see here a comparison between the, on your left, is a comparison between the JR curve for the SCT, you are the same, okay, and the SEB. You can see here the difference. Okay? With 1 millimeter of crack growth, I have almost 600 megapascal millimeter. Okay? If I compare this to the SEB, it's 230. So it's almost 1/3 of the toughness. Okay? And measured using, this is for X80 pipeline tube, using SCT specimens. Here, okay.
Why not using a surface semi-elliptical crack?
Sorry, can you say it again?
Why not using a surface cracked with a semi-elliptical flow?
Oh, because it's much more difficult to test. Okay. This is for one thing. The other thing is, I know whether again you are right, okay? Because the defect in a pipe is actually surface crack, it's not straight, okay? But then you have to test many combinations of surface crack geometry. That makes it very difficult, okay? But you are not wrong, you're correct, okay? The SCT is first easier, okay? And at the same time has the level of constraint very similar to the pipe. So actually we are very comfortable with this, okay? And here is what I said about the plasticity, okay? Let's hope this works. Aha. Okay. You are going to see that it's the pipe and the SCB. It's the 3-point bend specimen. Okay? So at the beginning of load, you are going to see the red zones, because I don't have, no. You see the red zones are the means stress contours. Okay? So at the beginning of load, you are going to see that it's very similar. Okay? Cool. That's very strange. Anyway, okay. You're going to see here, okay, at the beginning. So when okay, at the end of loading, you're going to see that the plastic zone is spread to the surface, while for the SCB, is very confined. Okay. Guess what? The stresses here are much smaller, the corrective stresses, okay, are much smaller than the stresses in here. Okay? Now let's see the SCT. Oh, by the way, I can send you the movies later. Okay? I'll talk to Professor Riggs, and then we sort out any way of distributing additional material. And this is the pipe and the SCT. See, the same crack size. Okay? No? This is a little tricky. Okay, I'll just let that leave it. Just stop. Okay, you see they are very similar. Very similar. Again, I'm not sure if you are familiar with that. Okay, because another 2-parameter characterization of the crack is the T-stress. Okay, so when we compare stress fields like this, then we say that the T-stress here is similar to the T-stress here. Okay, and that's the reason why the SCT is easy and you don't need to do any surface crack. Very good. Very good.
Here it works for high triaxality.
This is not high triaxality. This is, I don't know why can I stop here. Should stop. Okay. Okay. Yeah. Go on.
Yeah, it looks like high triaxality.
No, but it's not.
Okay.
Oh, it is not. Yeah. How do I know? How do I know? Because the angle of the plastic zones. I don't have it here, but if you go, Ted Anderson's fractal mechanics book, are you familiar with Ted Anderson? Okay. You're going to see the plastic shape on the plane strain, high constraint deformation. You're going to see that's has a very typical shape. Okay? When the triaxiality is smaller, the plastic zone start to tilt. So actually you can see here. This is the SCB. The SCB is like this. Here. See how different it is? Okay. And you can see clearly the development of a very negative T-stress. Here. It's very different. Okay? And this angle, the more the less triaxiality it has, the more angled is these, the more spread is these, the plastic zones. Okay, that's the way. Okay, let's move on. Again, this.
So my question was, so the similarity of conservative of the SET is valid for both the plane strain and plane stress.
Yeah.
Okay.
Okay. Yeah. This is plane strain, but plane stress will be the same. Probably the stresses will be a little different because of it's plane stress, but the similarity is the same.
Okay.
Okay? And as I said, this is similitude. So the similarity between the SCT and the specimens. Okay, I'll just go overview because this is a little too much details about the procedure. Okay, how do we evaluate the procedure? Because the thing with the SCT, it's not a standard specimen. It's not. Okay, Breed Standard has recently published a standard. But it's not complete. Okay, so for let's say there are no complete standards whatsoever. So usually the oil and the industry usually they have their own procedures. Okay, I'm just going very quickly. How do we evaluate this? Because we are a little delayed here. But, so the thing is that what we need to do is to evaluate the resistance curve. This curve. Okay. This curve here. But we need to evaluate this for the assessment. Okay? So how do we evaluate this? This is a very simple procedure which relies on the variation of the specimen compliance. Because we want to measure. Okay? We go to the level and measure. Don't put a camera there, don't put like a deep test, sometimes a high resolution camera. But here we just measure the variation of the compliance, which is like this. Okay? Here. We load, unload. Load, unload. Okay? Load and unload. And since the cracks is growing, okay? Since, you cannot see with your naked eye, of course, because the variation is very small. But it's varying. Okay? The slope of the elastic unloading is varying. So we correlate the variation in the elastic unloading with the variation crack size. That's how we usually do. We can use other techniques, of course. For example, torque potential. We can just set up an electrical device, and then we can measure the resistivity. Because when the crack is growing, the resistivity is also changing. Then we just calibrate the change in resistivity against the change in crack growth. Okay? But usually we don't perform a physical crack growth measurement. Only the final, at the end of the test. At the end of the test, we break the specimen and we measure. Okay? Just to show some data, because this is just data. Okay? To show you, as I mentioned, the undermatch. Okay, so this is a X65 pipe clad with the Inconel 625. Okay, and that's the stress strain behavior here. So the Inconel alloy has higher hardening but lower yield stress, and the base plate materials, the X65, has higher yield stress and lower hardening. So you see here that the mechanical behavior is different, and this will impact the assessment. Just to give you an idea how is the test conducted. Okay, you are going to see the unloading. It's not fatigue. No fatigue loading. Okay, this is increasing load. Just in one load, let's stop it. Okay, here the cracks propagating, you see here. Okay. Let's keep this. We don't need it. These are details about all the the parameters that we evaluate. Okay, let's skip this. Just to give you an idea, what enters the assessment. You can see here the crack is growing, and nowadays, for those more interested in numerical prediction, nowadays we have very good numerical tools to predict the depth criteria in this kind of material and this kind of, okay. Okay. How much time do we need?
2 minutes.
Sorry?
Yeah.
Okay. Just to show you the observation here, another thing that we need to care about, again, is the mismatch, okay? The driving force. So what I showed you before is the specific details about measuring the fracture properties. On the other side is the crack driving force. It's a very important ingredient. And again, we have the similar weld material here. Okay? So the procedure that is, I'll go very quickly, just to show the final result. So the procedure that we have here is kind of obtaining an equivalent material. It works like this. You have the similar weld. So you apply load, you measure displacement. So what would be the homogeneous material that would give you the same displacement with the same applied load? That's the idea behind this. It's a little complex. We use lift load analysis, slip line calculations, etc., etc. What's important is this. Okay, simple case like this. We have the stress strain curve, and this is what we would get. Okay, the tolerable crack size. Just to give you an idea, this is my last slide. Okay, here is API 579, for example, for a crack length, a crack size with 100 millimeter length. Okay, the maximum, the tolerable depth would be 2.2 millimeter. If you use the advanced procedure, take into account detailed finite element analysis, equivalent stress strain relationship, etc., 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 you'd get more than double the tolerable crack size. So you see a very huge saving in your installation process because your tolerable crack size is much more refined. Okay. Okay. I have more things here, but
Okay, thank you very much, Professor Claudio Ruggieri. Very impressive lecture. So I think we don't want to kill our students. So I don't know if you have any kind of question or comments. Well, just to finish 2 or 3 questions.
Hi, so when you're reeling and unreeling the pipe, yeah, that's a good.
how are you doing with it?
Yeah, good, thank you. So when you're unreeling and reeling the pipe and you're in high constraint load, do you have to consider a high constraint toughness at that point?
It could be.
Yeah.
Also, the procedure, I didn't go into detail, but it's really important. The procedure, the very level of the procedure does allow including all sorts of things. Okay, does criteria analysis, changing the mechanical properties, softening and level 3, rest procedure, it's up to the contractor and the client, let's say, to decide what would be the best approach for
In case of anisotropic elastic materials, is there some easy way to analyze it except going through difficult FEM?
I think it's, you see, we avoid most of the time to go into very detailed 3D financial. This is 3D financial, it's not really. It's time consuming, can somehow use a kind of log mixture or something like this that will be close to your previous financial net, that's fine. Okay? So that's the way to go. You need to come up with a code which I'm not aware of. And then compare it, validate with either experimental data and financial data. Okay? But sometimes you don't have any choice. Running financial data.
Okay, I think now just a question there, no questions on this side, so just this side now and to finish. I think this okay, all right.
Thank you for the presentation. Do you think that if we include in the calculation, for example, the Gerson model and include the parameters of Gerson damage model,
Yeah.
that could change the result that you just showed, or
Yeah.
they will be the same?
No, you can. Actually, one of the points that I showed you was obtained by Gerson model. Okay, so actually you do use Gerson model. You know the Gerson model is not
Yeah.
100% perfect.
Of course.
You know,
Yeah.
okay? It has many drawbacks.
Just
that-
you. Can you take best, please? So the last question.
Okay, just really quickly, when you're using a specimen geometry like SET that has inherently shorter ligament length, do you or how do you account for in-plane constraint loss when you're putting more and more displacement on the specimen?
I'm not sure you understood, because the SCT is a specimen that we use exactly to match the constraint in the pipe. Okay, so for example, if the pipe has, let's say, 20 millimeter thickness, and A over T is 0.3, that means your crack size would be 6 millimeter. 6 millimeter, and the ligament would be 14. Okay. The SCT will reflect that, if that was your question.
My question was more about when you have a shorter ligament length,
Okay?
you start to experience in-plane constraint loss of the crack itself, not the...
Okay. I think I understand. Okay, then we can talk later. But then probably you are going to the failure mode of classic collapse, because probably your R curve is not capturing what's happening. Because you see, we don't go more than 3 millimeter crack growth, 4 millimeter. If you grow the crack too much, then probably you are going to lose constraint, or you're going to enter in another regime of failure. Yeah.
Okay, well, I think now we need to finish. Again, thank you very much, Professor Claudio Ruggieri, for your presentation.
Just a final remark. So, for those that are still waiting for the certificate, those are prepared outside. And also, before leaving, we have some sandwich there at the left door. So please feel free to go there and pick one. And see you later at the dinner at 8. Okay?
Sorry, do you have any question regarding, so we meet again at 8 p.m. in the restaurant Vivaldi, okay? And tomorrow morning at 9 o'clock we start again. Okay, see you later in the restaurant.
Okay.